Hello, everyone. Sorry we're late. How's it going? All hyped? Hello. Yo. Hiya. Hey, so today is about current and charge. Is this new stuff for people? Is this old stuff? Is this old news? Hello. Hello, hello. What are we up to? Thanks to everyone for coming to do physics at what is it, 6 p.m. on a Sunday? Well, it's in the UK anyway. That's proper commitment. Yeah, so today is about current and charge. It's quite a fun one because, well, there's some formulas, there's some math stuff to do, but there's some nice kind of what you call like qualitative stuff, so like conceptual stuff to chat about as well. So you get a nice range of questions. Okay, so we'll get going about 5 past. We'd be doing astronomy soon. Let me take a look. I will take a look for you right now. I'll just take a look. That's something you're particularly keen on, or have you got a mock coming up on 9th of October, maybe? What do I think about a second lockdown? Yeah, I wish I was more qualified to judge on the whens and wheres and so on. Yeah. You're doing the actual exams for your A-level grades. Oh, I see. Okay, cool. Yeah. Okay. Yeah, let me check the let me check my schedule. So at the moment, I think what we've yeah, I'm not sure at the moment. We're only doing these physics ones once a month at the moment, on YouTube anyway. There's a lot more on Stat Revise, of course. So we probably won't. I think we almost certainly won't be doing any stuff on astronomy before 9th of October. Sadly, good luck for the mock though. The exam. Good luck for the exam. Okay, cool. Hello. Yeah, how's it going? I wish I knew. I promise. I would tell you. I would tell you if I knew, but I think we're all sadly in this in the dark and a bit uncertain at the moment. Okay, I'm gonna kick us off and go on with it. Oh, hi there, Franklin. How's it going? Okay, so I'm just going to get us started. So today is a web class. So we're going to be, the way this is going to work is we'll be going through some concepts. I'll introduce some things. I'll ask you some questions. We'll see how we get on. Feel free to ask questions in the chat. It's absolutely great if you ask stuff, especially anything you don't understand, because that means I get to know how it's going and I can see what needs more explaining, etc. So yeah, any interaction is fantastic, so go for it. It's split into 2 parts, and at the end of each part we'll do at least one exam question to see if we're getting stuff. So I think that's enough blurb, so let's get on with it. First of all, about me. So my name's Matt. I was looking a bit more fresh-faced in that one than this one. That's a year of a PhD for you. And yeah, so I've been tutoring physics for a while, working with Stat Revise for a while, and looking forward to doing a bit more. So yeah, there's going to be some giveaways. There's going to be a free account for one for anyone who follows us on Instagram or shares a picture of our web class and our story. So go ahead, spread the word. And of course, there'll be coupon codes for some serious discounts, and we'll give that at the end of the session. Great. Okay, so let's get this party started. Adjectives: define terms charge and current. I'm sure a lot of you have seen them, but we'll go through them nice and slowly and methodically. Understand how charge is quantized, how it only comes in little bits. And finally, describe how current is caused by the movement of electrons. Good. Oh, okay. Hello from the UK. Thanks for signing in from so far away. What's the time there? Okay. UCAS exams. Nice. Okay. So what do we already know? So the way we like to start off these sessions is by recapping the stuff that we're going to need to know for today. So first of all, protons and electrons, two of the three important things inside an atom. So what's the third type of particle inside of an atom? And can you tell me any properties, any important properties of protons and neutrons? Protons and neutrons, protons and electrons. Thank you. Good. And where are they? Which ones are which here? We've got kind of, what are these red ones on the outside? So here we're looking at a picture of an atom. Cool. And what's it made up of? Well, it's made up of some protons. Those other particles were called neutrons. It's made from protons and also electrons. Now these things, these protons and electrons have properties called charge. Can anyone tell me anything about the charge of a proton and the charge of an electron? Maybe they're signs. Good, yeah. So electrons are negatively charged. So let's jot that down. That's going to be important. Negatively charged. What about protons? I see you already said. Yeah, protons are positively charged. Perfect. Positively charged. Good. Okay, so that's going to be important later. Second thing, what happens, what's the charge of an atom? You've told me electrons are negatively charged, protons are positively charged. What's the charge of an atom? One way you can figure it out is knowing that there's as many protons as there are neutrons. Good, so neutral, absolutely right. What happens to the charge of an atom if I remove an electron? I make an ion. Is the ion positive or negative? So I remove one electron. What happens to the charge? Goes positive, absolutely right. I've removed a negative charge, so what's left is now positive. Perfect. Okay, next thing is a circuit. So what I'm looking at here is a circuit diagram. Essentially, the black lines here represent wires. There's a special device. There's two special devices going on, one for creating current and one for measuring current. So this thing here, the thing creating current, very loose way of describing what it does. And really what it makes is a potential difference. We can give one end of it a kind of a positive sign, one end of it a negative sign, and then current's going to flow in this circuit. Does anyone know which direction, clockwise or anti-clockwise? Which direction is current going to flow here? If I've labeled this bit as positive and this bit as negative. So I guess my question is, does current flow from positive to negative or negative to positive? Good, so current always flows from the positive terminal to the negative terminal. And so it goes like this. It starts at the positive, tries to get away from positive until it makes its way into the negative. We give current the symbol I, so I'm going to call that I everywhere. And what's this? So this is clockwise. And what's the name for the device that measures current? No, I don't think we will cover much proper stuff about EMF today. Yeah, good. This is an ammeter. Good. Okay, so this is the review stuff. This is the stuff that it's really good to know coming into this session. I really wish I'd written Amita better there. Sorry about the handwriting. Okay, cool. Good. So I'll just kind of knock us through the spec points for now. Here we go. So here are the specification points from the various exam boards that we're going to go through today, and then we'll start the session properly. Okay, so the important things are these kind of definitions, especially the definition of current. The idea that there's some kind of elementary charge is also an important thing. And for some of the specs, we're going to want to know this equation at the bottom. And I'll point out which specs and what equation when we get to it. Good. So we're going to start off by really going from the ground up, making sure we've got everything down. So let's start by talking about charge and current. So what's charge? So charge is some kind of, let me say it like this. Charge is an intrinsic property of an object. Intrinsic property of an object. Essentially, it's a property of an object that was going to determine how it behaves with some other objects. The way they behave, the way that they behave with other objects is going to be described by something called an electrostatic force, a kind of electric force. Okay, so the charge is like a number that says how something's going to behave with an electric force, and it has some properties. Because it's a number, it can be positive. It can be positive. Now, you also mentioned that electrons had negative charges. So clearly charge can be negative. And we mentioned with atoms that things could have no charge. They could be neutral. So it can be positive, negative, or zero. We use zero charge to mean neutral, no charge. You're repeating Unit 2 at Excel. It's October, right time. No worries, no worries. Okay. Okay, so the classic stuff. I'm sure you all know this, so shout it out. So if I have two charges and they have like charges, by which I mean they're both, for example, positively charged, will they be repelled or attracted to each other? So I have two like charges here. Here they're both positive. They could have both been negative as well. What happens? Good, they repel each other. Fantastic. So charged objects will be repelled. Let me jot another L in there. Will be repelled from like charges. And what about opposite charges then? Good, they will be attracted to positive charges. Fantastic. Attracted to opposite charges. Fantastic. Okay, so just as a quick application, I've got a charge here inside kind of an electric field. It's between two electrically charged plates. Is this charge going to move to the left or to the right? Which way is it going? So I'm looking, sorry, I should be clearer here. I'm looking at this charge here. It's between this negative thing here and this positive thing here. Is it going to go to the left or to the right? Good. This thing is going to go to the left. It's going to be attracted to the opposite charge and repelled away from that opposite charge. Good. Absolutely right. Left. Absolutely. Yeah. You got it. You got it. I just can't say it. Right. So that's how charges behave. We have these electric forces that attract and repel based on the signs of these charges. Now we want to talk about the magnitude. We could talk about how hard things repel or how hard things attract each other. Okay. So we describe how hard things repel or attract by the size of the charge. It turns out that the charge comes in bits. There is an elementary size that charge can be. You can have no charge smaller than this amount of charge. Does anyone know what charge this is? It is actually, or should be, in the formula book, or the kind of Becker constants that you get for your exams. I'm afraid we haven't got anything organized for next week at the moment. Sorry. Everything that we have got, you'll be able to see on the YouTube channel. It should all be scheduled up. So there's an elementary size, there's an elementary amount of charge that you can have, and it's very small. So the elementary charge is called 1, and I'll explain exactly what I mean by this in a second. It's 1.6 times 10 to the minus 19 coulombs. Okay. So coulombs are the SI units for charge. I'll just jot that down. Coulombs. And I just want to jot this bit down to the left here, because this is important. Not only can I not have a charge smaller than this amount, but any charge that you can come up with is essentially made of some number of bits of charges like this. Any charged object, however charged it is made up of a load of little bits of charge of this size. So an integer set is like having a whole number amount of something. So all charges can be measured as an integer multiple of E. That's this number here. So whatever charge some object has, if I have some object here with charge Q, I know that charge Q is going to be equal to some number like 1, 2, 3, 4, the counting numbers, multiplied by the elementary charge E. It's just this number here that can vary. Okay, so does anyone know what the charge of a proton is in terms of this number E? Hello, hello. What's the charge of a proton? Is it this elementary charge? Is it 2 lots of the elementary charge, 3 lots, 4 lots? How many? So it's the same as the charge of an electron, but with another sign. Yeah, you're absolutely right. It's just 1 lot of E. So protons have a charge plus E. So you can't have a charge smaller than a proton. Okay, unless you do the particle physics stuff, and then there's quarks, but we don't talk about them for now. Okay, and then for electrons, we have minus E, because we know these things have opposite charges to each other. Okay, let's do a quick example. A neutral rod is rubbed with a cloth to remove electrons. It's a classic way you can generate static electricity, and give it a positive charge of 6.4 times 10 to the minus 19 coulombs. Calculate the number of electrons it loses. So what formula am I going to use? How am I going to use it? Help me do the question. You guys are my pen. What am I doing? Nice. The answer is indeed 4. The answer is indeed Q over E. Good. So we know that the charge, the total charge which they've given us, is equal to, well, in this case, how are we getting this charge? Well, each bit of charge that we're getting is due to having lost 1 electron. And we know each electron has charge E. So altogether, our total charge is going to be equal to the number of electrons we lost times the charge of each one. Okay, so we can rearrange this for the number of electrons we lost. Get N equals Q over E. Q is 6.4 times 10 to the minus 19. And E is 1.6 times 10 to the minus 19. These things cancel, and 6.4 over 1.6 is indeed 4. So we lost just 4 electrons. Good stuff. Fantastic. And thanks for giving the answer in the chat. Awesome. Well done. So next section, current. Can anyone define current? Easy peasy, indeed. Okay. Can anyone define current for me? Has anyone come across this definition? Doesn't matter if you haven't. Rate of flow of charge. Good. Okay. Electric current is defined as the rate of flow, or I guess another word we could use is or transfer, the rate of transfer. The rate of flow or transfer of charge. So it's like charge divided by time, or like change in charge divided by the change in time, the time it took for that change in charge to happen. Okay, so as a formula, how do we write changes? We write changes usually with the Greek letter delta. Okay, so current is equal to change in charge divided by change in time. Well, which time? The time it took for that change in charge to happen, not just any time. Okay, if charge is measured in coulombs and time is measured in seconds, what are the units? Well, I will tell you that actually the units of current are amperes, but what's another way of writing those in terms of coulombs and seconds? Good, coulombs per second. Coulombs per second. Fantastic. Why this hour? Yeah, good question. I guess that's just the way the scheduling's happened at the moment. That's probably the worst answer ever. It's just the way it's worked out so far. Okay, good. Coulombs per second. Coulombs per second. Fantastic. Thank you for anticipating the answer below. We will absolutely get to that. Now, often I think this is a really nice time to mention something about definitions of units. Often you'll be asked in an exam to do something like define coulomb, define the coulomb. And often it's not clear exactly what to do. It's something that I find a bit jarring sometimes. So a really good way to answer those questions is to find like one of the basic questions that unit appears in and define it in terms of that equation. I'll show you what I mean. So let's say I wanted to define the coulomb. Okay, the examiner said define coulombs. I would say, okay, well, I know it appears in this equation, current equals charge over time. So in fact, if I rearrange this equation and don't worry about the deltas, I've got charge is equal to current times time, roughly. Okay, then I would say, what's a coulomb? A coulomb, 1 coulomb should be what I get when this is 1, when this side of the equation is 1. How can I get that to happen? Well, I can get this to happen by having both of these things be 1. So I could have the current be equal to 1, and I could have the time be equal to 1. So I'll give a sentence now which defines what 1 coulomb is. 1 coulomb is the charge transferred, by 1 amp of current in 1 second. Good, yeah. So I just want to mention here how I got to an answer here. I was saying, how can I define a coulomb? And the way I did it was I found this equation that the coulomb is in, and then I rearranged it, and I set everything to 1. And then I knew I'd just get 1 coulomb out. And that was a way I could then put into words what a coulomb was. It's what I get when I have 1 second and 1 amp. Good, okay. Charge transfer per unit time. Good, that would be a definition of the amp. That is a unit for current. Good. Okay, so let's have a go at a question. Calculate the current through a wire if it takes 18 milliseconds to transfer a 1.4 coulomb charge from one end to the other. So what are we being asked to calculate here? The current. So we need a formula for current. Can anyone give me the answer? Per means divide. Really good. When you have like one thing per unit something else, they mean the first thing divided by the second. Nice. Okay, 77.8. Good, so let's see how this works. We're trying to calculate current. Current is change in charge divided by change in time. The change in charge is 1.4, and the change in time is 18 times 10 to the minus 3. Why did I put a times 10 to the minus 3 there? And that is indeed roughly equal to 78 amps. Good. Yeah, times 10 to minus 3, because always check for the units. This was milliseconds. And how do I measure the current? I think you guys already told me this one. But what's the answer, just for my fun? It's this thing, isn't it? So if I want to measure current, I do it using an ammeter. And that's all you ever need to know about current ever. And that's a lie. Of course, there's more to learn, but that's a good start. Okay, so how's everyone feeling? 0.018, 18 divided by 1,000. Yeah, that's right. All the exam boards are good. So we're covering the kind of big three here for the UK. So we're specifically covering OCR, AQA, and Edexcel. All of them great choices. I'm seeing a lot of ones. Nice. Good. Okay. Number 2, also great. If you have any questions about the content we've gone through so far, just let us know. In the meantime, I'll kick us off on some questions. So, okay, what's meant by electric current? I need a definition. So it's a classic exam question. Is you just asked to define current. Ah, I see. Yeah. So yeah, I can totally recommend OCR, Edexcel, AQA. All great shouts. Okay, so what's the definition of electric current? It's the rate of flow of charge. Rate of flow of charge. Good stuff. The standard index unit of electric charge is the coulomb. Define the coulomb. So now we're being asked to define a unit. And these are those kind of ones that, like I was saying before, can maybe feel slightly more jarring. You're being asked to define a unit. You always end up having to define it in terms of something else. Standard index unit is the coulomb. Define it in terms of something else. How can we do it? I'm not sure about electric field stuff. I hope we'll get a chance to do it at some point. We're only doing so many things on YouTube. We try and go through absolutely as much as possible on Start Revise, and then we do this kind of like once a month thing on YouTube. Yeah, when good. So we've got this. You may remember I was saying that there's this awkward kind of question you often get, and one way to answer it is to think of the equation. Think of the important equation that quantity comes up in. So it's a coulomb. It comes up in the current equation, and translate what 1 coulomb would be into words. So, okay, I know that charge is equal to current times time. So 1 coulomb is the charge transferred when 1 amp, let's say by, that's easier. Charge transferred by 1 amp of current in 1 second. Okay, good stuff. Good, really nice. When 1 amp passes a point in 1 second. Nice. Okay, question number 2 is going to be a more of a mathsy question. We've got to compute something. So figure 1.1 shows 2 strips of aluminium foil connected to a DC supply. Cool. Switch S is closed. The charge flow past a particular point in one of the aluminium strips is 340 coulombs in a time of 50 seconds. Calculate the current in this aluminium strip. Notice a lot of this question is actually not relevant for our answer. There's a couple of key details. There's 2 numbers we've been given. We need to know what formula to use and what the answer should be. So, what formula am I using? What should I use? 6.8 amps. That is indeed the correct answer. Good. So they're asking me to calculate the current. So immediately I should write down the definition of current. It turns out the definition is all I need, because the definition is in terms of a change in charge and a change in time. We've got them both down, so we're in. Absolutely textbook stuff. 340 divided by 50. Good. Yeah, really liking seeing those formulas. Fantastic. And those rockets. The examiner probably doesn't need to see them, but I'm more than happy to accept them as part of the answer. Okay, so this is indeed 6.8 amps. Good. Yeah, we will be accepting rockets. Good. Final question. Yeah, it should be. All the recorded stuff should stay up as being watchable later. Yeah. Okay, part C. A digital watch uses a 1.3 volt cell. It delivers a charge of 650 coulombs at a constant rate during its lifetime of 1.6 times 10 to the 7 seconds. Calculate the current. Okay, feed me an answer. I've been given some extra stuff this time. There's also a voltage. I've been given a voltage. I've been given some coulombs. Okay, so I've been given some charge. I've been given some time. Ah, I'm glad. No worries. Yeah, come by any time. Okay, so what are we doing? I need a formula. Of course, it's the classic formula. Current is equal to change in charge divided by change in time. Has anyone got a number for this? So what's the change in charge? It delivers 650. Let's see if you guys are right. Delivers 650 coulombs. So that's the right units in 1.6 times 10 to the 7 seconds. Okay. Good stuff. And what are we getting? 4.1 times 10 to the minus 5. Good. Yeah, I really like that. So this is roughly equal to 4.1 times 10 to the minus 5. And what's the units? Of course, the units are amps. I'm really sorry to hear about your AS exams. I'm sure a lot of people are sadly in this in this situation. Yeah, good. That's a good answer too. 4.0625. That's the detailed answer. We'll also be taking that. Good stuff. The total number of electrons passing through the cell during its lifetime of 1.6 times 10 to the 7 seconds. So how do I find the number of electrons that make that much charge? What equation is that? That's going to be a different one. Sometimes you get lucky. You're right. That's a very kind 3 marks. Absolutely right. 4.1 times 10 to the 21. Good. How did you do it? Good. E equals Q divided by N. Fantastic. So good. We have Q equals NE. Charge equals number of electrons times the charge of each electron. Good. So then the number is equal to the charge divided by the charge on an electron, which is equal to 650 divided by, what's the charge on each electron? 1.6 times 10 to the 7 seconds. Good. And altogether, that's 4.1 times 10 to the power 21. Well done. Good stuff. Okay, so we've kind of done some formulaic stuff, some stuff for numbers. So let's do some more qualitative stuff. So now we're not just thinking about static charge, how much you have. Well, we started there, then we talked about motion of charge in terms of current. Now we're going to understand a bit more of the details of current in terms of motion of electrons, because there's a kind of detail that we've been missing so far that's quite important. So, okay, so can anyone tell me anything about the structure of a metal? That's a complete tangent. What's the structure of a metal? Those of you doing chemistry in particular. Tell me stuff about the structure of a metal. Can we find it by I times T over E? Let's see, I times T over E. Absolutely right, you could have done that. Good. That I times T that you'd have got would have been Q. Good, we got some kind of a lattice structure. Everything's tightly held together. Okay, what's in the lattice? What makes up the lattice? Is it like the positive bits or the negative bits? Nice. Okay, we've got a lattice of positive ions. I like that. That's what we're seeing here, actually, this lattice of positive ions surrounded by delocalized electrons. Okay, delocalized, that's really cool. What does that mean? That means they can move around. That's exactly how we're able to have currents in these things. Electrons are able to move around in the material. So charges can move around, and that's how we get currents. Okay, so metal conductors. We're going to try and understand a bit more. We're going to zoom in with a microscope and look at current. So metal conductors. Metal conductors are lattices. Lattices, that probably is, lattices of positive ions. Good. Okay. And we've got these free electrons. You mentioned these free electrons. Free electrons can move around. They can freely move between the ions. Now, here's a key question. If I tell you this is a piece of metal wire here, and I tell you there's no current, the current is 0, do you think the electrons are moving or not? We get some votes in the chat. What do we reckon? Do you reckon the electrons are moving or not? Already got some controversy. Good. This is what we want to see. We've got a no and a yes. We've got another no, another no. Any more for yes? Oh, moving. Okay, that's 3-2. Go on, take a punt. Take a punt. No. They are. Okay, cool. Right. So clearly we have some disagreement. The answer is yes, they're moving. Probably at any finite temperatures there. If we've genuinely got temperature in all normal situations, these things really are moving. Okay, so let's make sense of this, because current is supposed to be the rate of flow of charge. So surely if the charges are moving, there's a current. So since current is rate of charge, there's no currents and no electron movement. Yeah, exactly what I was just saying, right? So what's gone wrong here? Okay, they are moving, but in random directions. This electron's moving like this. This electron's moving like this. This electron's moving like this. Random sizes, random directions. On average, there's no net movement. On average, there's no velocity, but each is individually moving. Good. So there's a difference between this thing called like drift velocity, which we'll come to, and each individual velocity. So the answer is there is motion, but it's random. Motion of electrons is random, so no current. So yeah, not quite. They still move a bit randomly, but they'll have a general direction as well. Here, there's no general direction for the electrons. It's just complete madness. And that's why there's no current. Okay, so let's imagine now apply potential difference. We apply a potential difference. Okay, we apply a potential difference. So we make one end positive and one end negative. Where are the electrons going to be attracted? To the right or to the left? Yeah, just like how things randomly vibrate, really at room temperature. That's a really nice, it is really that kind of thing. There's all this random motion. Good, these electrons are going to all move. They're still going to have some random stuff going on, but it's all going to be generally more to the right-hand side. You see, like there's still a bit of up and down and stuff, and there might even be the occasional one moving the other way, but there's now a general net movement, average movement to the right-hand side. Good. So net is a fancy word for average. Net movement to right-hand side. Good. So current is not equal to 0. This is what it means for the current to not be 0. There's a net, there's an average, there's a drift to one direction. So, good, absolutely right. Yeah, good stuff. So there's loads of electrons. Okay, so finally now we have to do some maths for this stuff. So we're going to do some maths in terms of these like macroscopic details. If you're doing AQA, you're lucky you haven't got to know this, but I do recommend just listening anyway because it's kind of cool and it might help you understand the conceptual stuff, which you did need to know. Okay, so there's a thing called the transport equation. Has anyone seen it? If you have, maybe you can beat me to writing it down, or you can tell me what the quantities in the equation mean. So I'm going to say this. I is equal to A, what's A, times N, what's N, times E, what's E, times V, what's V. Okay, so this is a formula for the current in a wire. A wire with a cross-sectional area, A, with a number density, N, of the charges. So that's the number density, that how many electrons, for example, how many charge carriers you have per volume. V is the average velocity of these things, and E is the charge of each of these carriers. Could have been, for example, 2 lots of E or something. So we've got these four different quantities. Good stuff. And let's see if this makes sense. Okay, so if I have more particles, if I've just got a greater density of charged particles in my wire, then yeah, I can imagine I'd have bigger currents in general. If everything's moving faster, so let's give this a proper definition. This is the mean drift velocity. If everything's moving faster, then we'd expect the current to be bigger. Current is rate of flow, rate of movement of charge. So let's define this thing. Mean drift velocity is the average velocity of electrons as they drift. What's this drift? The drift represents this kind of, they're moving randomly, but they're roughly going in one direction. They're drifting as they drift through the conductor. Okay, electron number density, that's this thing here. Can anyone give a density of electron number? Can anyone give a definition, slightly tired, of electron number density? Because it's not quite the number of electrons. There's an extra caveat, there's an extra bit that we need to say. Electron number density, what's this density bit? This number here is probably adding something to the definition. So electron number density is the number of free electrons, so the ones that can actually move around, the number of free electrons per unit volume. Per unit volume. And someone asked a really good question earlier. They said, does X per unit Y mean X divided by Y? Absolutely. So one way of saying what this number density is it's the number of electrons that you have divided by the volume. So it's just, yeah, it's electrons per unit volume. Good. Couldn't have put it better. Didn't put it better myself. Good. Okay. So again, if we've got more electrons per volume, we should have more current. If we've got a bigger area, if we've got more, if it's kind of, if there's more space for electrons to move through, yeah, maybe we have more current. Okay, if we have bigger charges, then we have more current. And if everything's moving faster, we have more current. So all the proportionalities in this equation kind of make sense. Okay, how's everyone feeling about that? I think I don't quite understand your question. What is the conventional movement of electrons? Do you mean like what's how does movement of electrons compare with like conventional current direction? Because yeah, I think if that's your question, the answer is it's the opposite direction. Electrons move one way, the current conventionally moves the other way. Good. 1, 1, 1, 1, 1. If the volume is bigger, does the current increase? If the volume is bigger because the area is bigger, yes. Depends why the volume is bigger. If the volume is bigger because the length is bigger, no. Good. Okay, cool stuff. I might get back to your science teacher question at the end. I don't know if I can answer that so well right now, or generally actually. Maybe I can think a bit more about it at the end. Live is really helpful. You're learning a lot. Awesome. Yeah. You don't get the mean electron bit. Cool. Yeah. Let's just take a look. So I'll just say a quick thing. Okay. Mean drift velocity. So mean drift velocity of the electrons is the average velocity of the electrons. So if I go back to this picture here, and let me try and clear this up a bit. Okay. Let's say I've got this electron moving up in this direction, call that V1. Here's some other electron moving with V2. Their average velocity would come from adding these two together. So notice one of them's going up, the other one's going down. I could find the average by adding these things together and dividing by 2, for example. And I'd just get something that moved in this direction. I'd get like V1 here plus V2. And I just get this kind of mean flow to the right. So mean comes from adding together all the velocities that are in your wire. Good. Okay, so let's have a go at some questions. And of course, let me know if there's any more questions. So the wire is connecting a there's so many numbers in this. Okay, so strap in. There's a 36-watt lamp, 12-volt battery, made of copper. They have a cross-sectional area. Okay, so we're going to be using that area current equation probably. There's already this hint here. Okay, current in the wire is 3 amps, number n of 3 electrons per volume. Cool. Copper is this many. Describe is what is meant by the mean drift velocity. Okay, hit me with a definition. I gotta have a definition. Who can anyone remember, or even just roughly? Absolutely, just give it a crack if you're not sure. What do we reckon? Okay, I will give us a go. Oh, 1 second. Drift velocity is the average velocity of electrons as they drift through the conductor. Good, that sounds really nice to me. So let's just jot that down. Okay, sorry, just had a slight tech malfunction here. Average displacement, mean velocity. Good, okay. So I'll jot it down here. The mean drift velocity is the mean just means average. So it's the average. The average what? Is it going to be The average mass, the average displacement, the average acceleration. No, the average velocity. The average velocity of free electrons drifting through the wire. Drifting through the wire. This free electrons a bit. The freeness of them is important. Good. Okay. Calculate the mean drift velocity of the electrons in this wire. Hit me. What formula am I going to use? I want to calculate what formula does the mean drift velocity even appear in? We only know one formula that it's in. So that's fantastic news. If you're asked something about mean drift velocity, you know what formula you're going to need. So we had this one formula that said current. Whoa, no. Current would be equal to, what was it? ANEV. Maybe in a different order. Okay, we want V. Okay, so let's rearrange. V equals I over ANE. Good stuff. Okay, now we just got to plug numbers in. Good. Okay, so what have we got? We got 3 amps of current. That was here. We've got an area. What's the area? 1.1 times 10 to the minus 7. Okay, good stuff. What next? We need a number density, which is 8 times 10 to the 28. Okay, I need a bigger fraction. Okay, multiplied by E. What's E? E is 1.6 times 10 to the minus 19. Because E is supposed to be the charge of the charge carriers. And here, the charge carriers are free electrons. Good. Okay, yeah, good. The transport equation, absolutely right. And 2.1 times 10 to the 3. Couldn't ask for a better number. That's exactly the number I wanted to see. Good. 2.1 times 10 to the minus 3. What's the units? Did I get the units right? Yeah, down here anyway. Meters per second. Good stuff. Okay, next question. The current I in a conductor is given by the following formula. Okay, what quantities do N and V represent? I won't write them down. They are the electron. Okay, I'll do it. Yeah. The electron number density. Number density. And mean drift velocity. Good stuff. Yeah, absolutely right. Remember, not just really good guess, not just quite the number of electrons. It's really tempting because of that M, number of electrons per volume, which is called the electron number density. So they really want to see that word. Cool. Okay, part B. A student has a metal conductor and a plastic insulator of the same dimensions. Okay. Applies the same potential difference across each. Explain how the relative values of N for the metal conductor and plastic insulator affect the current in each. Wow, so this wants a diagram to try and understand what's going on. Metal conductor, plastic insulator, okay. Potential difference across each. Explain how the relative values, okay, of N for the metal conductor and plastic insulator affect the current in each. What do we think? What are the relative values of N? Are there more free charge carriers in the metal or in the plastic? Because they're asking about N, which is essentially the number density of charge carriers. So there's going to be, we know that the whole thing was metals were these things that have these free electrons. Essentially insulators like plastics are things that don't have many. So yeah, the metal is going to have more electrons. Nice. Okay. So explain how, and they've asked us for how to explain it in terms of the relative values of N. So first statement is which N is bigger. Okay. N is bigger for what? Well, it's bigger for the metal. So since, okay, how does this relate to the current? Because they're interested in the current. Well, this equation is perfect then. This equation tells us that I is proportional to n. So since I is proportional to n, I is bigger in the metal. Look at that. Nice clean marks for 2. Nice clean answer for 2 marks. All right, final question. Is it legitimate to write about electron number density, assuming there is an electrolyte? So here it would have absolutely, electrolyte where ions are the charge carriers. Yeah, but you would have to change a word. Rather than calling it electron number density, you would call it charge number density. Then you'd be rosy. There are more charge carriers per unit volume, and therefore there will be more current as well. Good, really nice. Okay. Right, we have a final question. I'm afraid we're going to run slightly over. I hope that's okay with everyone. Anyone who's got to sign out, absolutely thanks for coming. It's been really fun doing this session, and I hope I get to see you at the next one. But I'll just take us to the end. So this is a more mathsy question. A student, and of course at the end, remember to stick around because we've got a code for coupons and so on. And I'll give you a little tour of Snap Revise as well. Anyone who wants to see that. So, okay, a student connects 2 pieces of copper wire, A and B, in series with each other and a battery. The diameter of wire A is twice that of wire B. Calculate the ratio of the drift velocity in wire A to the drift velocity in wire B. Explain your answer. All right, so I want to know some things. I want to see a diagram because I'm struggling to think about what this question is even about. So I'm going to draw a picture for myself. Also, what formula is this question about? They've mentioned drift velocity. So this question must be about that equation. I equals N, what is it? I've forgotten it myself. No, A, there's an E, there's an N, and there's a V. I think I've written it in a different order every time. Anyway, it's about this equation. Is there any important words here? Okay, 2 pieces of copper wire in series. Transport equation, absolutely right. Really, really happy to see that equation coming up. Good stuff. I've got wire A and wire B. Okay, cool. Okay, and they're in series. So let's draw them like this. There they are, kind of connected in series. Wire A. Okay, I'm going to have to use a different symbol for area. I'm going to use lowercase a for area because they've told me about wire A, and I want to draw this on the diagram. Diameter of wire A is twice of wire B. Okay, there's A, there's B. The diameter is twice as big here. So the diameter of wire A is twice the diameter of wire B. Oh wait, diameter is one end to the other, isn't it? Oh dear. There we go. Okay, cool. So calculate the ratio of the drift velocity in wire A to the drift velocity in wire B. Okay, so what's really important is if I want to calculate the ratio of these things, I need to rearrange for that quantity. So let's get this equation in terms of the drift velocity. V equals I over A E N. Okay, remember A is the cross-sectional area, E and N are these kind of number densities and so on, and we have this current. Okay, if I have a current going through this first thing and it's connected in series with this other thing here, what can you tell me about the current going through A and the current going through B? Well, they're going to be the same because they're connected in series. So the current for wire A is going to be the same as the current for wire B. Yeah, current remains the same. Really nice. Okay. So here's the idea. I want to figure out the mean velocity for wire A. I want to figure out the mean velocity for wire B and divide them. So that's going to be the current for wire A divided by area of A, charge in A, number density in A, divided by all the same stuff for y of b. So it seems complicated, but things are going to simplify. And b. Okay, so I just need to take some factors out of this equation. Yeah, series connection, absolutely right. Okay, so this gives me IA times AB, EB, NB, and then we'll try and make sense of this because I know there's a lot of symbols here, but stick with me because it will get nicer. IB, AA, EA, NA. Okay, cool. So we already said those currents are the same, so they disappear. What else can we say? Two pieces of copper wire, because they're the same materials, they're going to have the same numbers of free electrons in them, and the charge carriers in both cases are free electrons. So the size of each of the charges in wire A is the same as each of the charges in wire B. Similarly, the density in each is going to be the same. They're the same material, just made into different shapes. So these number densities are also going to be the same. So actually, suddenly everything's cancelled out and the ratio of the velocities is just the ratio of the areas. So, okay, let's see how this looks. Well, what's the area of the cross-sectional area for wire B? Well, it should be pi times the radius of this circle here, pi times the radius of B squared. And for the area, cross-sectional area of A, well, that would be pi times the radius of A squared. Now we could express that in terms of diameters instead. The radius is half the diameter, pi dA over 2 squared. And the great thing is, if we expand this out, maybe I'll give you a bit more of a chance to do this in your own time, to just go through the maths, because I've kind of gone through the maths quite quickly here. I appreciate that. Then all these numbers cancel out, and you just get the diameter of B squared divided by the diameter of A squared. And now we're ready. So this is a hard question. Now we're ready. So the diameter of wire A is twice that of wire B. Okay, so this is diameter of B squared divided by, well, diameter of A is 2 lots of diameter of B. So that's like that. And again, we can factor out these dBs. I'll let you kind of go through the maths a bit more slowly again in your own time. And altogether, that's 1 over 2 squared, which is 1 over 4. Wow. Okay, so there's a lot of maths, a lot of algebra in that one. So I hope that was okay for everyone. Feel free to ask any questions. But that's going to be the ratio of the mean velocities. So yeah, I hope that was useful. You should now be able to define the terms charge and current, understand that charge is quantized, and work with formulas and concepts about how charge is caused by the movement of electrons. Remember, even when there's zero current, even then, there's still movement of electrons. It's just completely random. Okay, good. So, I hope that's useful. Remember, we have some coupons knocking around. So do you have any questions for me? There will absolutely be more live videos, yeah? And loads more videos on the Snap Revise website, which we're going to give a coupon for. So I'm just going to, for anyone who's interested, I'm going to give a little Snap Revise walkthrough now. Okay. Let's just log myself in. Okay. Sorry about this, just 1 second. Okay, ever so sorry about this, just 1 second. Yeah, but absolutely hang on for the coupon code. Hi there. Yeah, I think this video is absolutely gonna stick around afterwards. Sorry about this, just 1 second. Hi there. Yeah, there absolutely will be some more live videos on YouTube. I'm afraid I've had a bit of a nightmare and I'm not able to get into my own SnapRevise account. So I'm just seeing if I can get myself a free trial. My apologies for this. Has anyone got any questions about SnapRevise while I do this? Seeing as I've got a little bit of time. Anything you want to know, I can have a crack at trying to answer. Aha, hello. Read the question you asked before. Your question is up. Will there be snap revise session for maths and chem A levels as well? I don't know off the top of my head. I was so the best thing I can suggest doing is subscribing to, yeah, thank you very much. Subscribe to the snap revise channel and you should get notifications whenever we set up a new live event. If you want to see more web classes and so on, at the moment for physics for AS and A level altogether, we're doing, let me see, we're doing 5 sessions a week on the actual SnapRevise website. And then once a month, we're doing an extra one on YouTube. So there's loads more physics web classes and so on. Okay, so finally managed to sort my account out. Sorry about that, everyone. So I'll just log us in now. Aha, awesome. Sorry about that. Damn it. All right, we're in. So I'm gonna give you a little look. Thank you so much for sticking around, people. I hope it was a good session. I remember you saying there was another Mike from Sorted. I'll have to look that up. I remember, yeah, Cupcake, you said there was a question. What are the steps to answer long, wordy questions? Ooh, I'll have a think about that. Yeah, steps to answer long, wordy questions. I'll have a quick think. In the meantime, yeah, so I'll do the walkthrough, and then just as I give a coupon, maybe I'll have a little think. Even if you're not around, that's okay. You'll be able to see this recorded or something. Okay. So here's the good stuff. Okay, so as you might be able to see right now, I'm set up on the Snatrify's website. So I've got myself an account, and I'm lucky because I've got the ultimate account. I'm particularly interested in physics, so I'm going to go to my physics course. I just want to give you a little view about how we do things on Snatrify, because one side of things is like the web classes, like what we just did today. And I'm really enjoying giving the web classes. As I said, me and my friend, my co-worker Kriti, share the sessions, and we do another 5 web classes a week. And I'll tell you a bit more about how they're set out, because they're not all like the one we did today, actually, although some of them are. Okay, so let's say I'm on Snatrify. I want to try and work on my target grades for A-level. I expect that's a lot of you. So let's find something I'm interested in learning about. And what were we talking about today? We did some electric stuff. So electromagnetic radiation, maybe. Collisions of electrons with atoms. What do we want? Yeah, let's do some mechanics. Scalars and vectors, why not? Okay, so the first thing I do is a diagnostic quiz. The point is that you don't want to spend time learning stuff you already know. That the quicker you can learn stuff, the quicker you can A, work towards your target grades, and B, stop revising and go out and do other stuff. So the idea is we start off with a quiz, and that will direct your learning. That will point you towards the sorts of things that you actually need to work on. So I'll just take us back, actually, because I think we can do a longer quiz to get a better idea. We're going to do particles and antiparticles. Why not? We start the diagnostic quiz, and we get asked some questions. Ordinary matter is made up of what? Let's see. Protons, neutrons, and electrons. Yeah. Okay. Now there's going to be a range of questions. Some of them are quantitative. I'll allow myself to get some of them wrong, which is my cheat way of saying I can't think of the answers fast enough. The cool stuff is going to happen at the end of the quiz. That's when things really pick up. So let's make sure I get something else right. Minimum energy. I can't remember that off the bat. 1 point. Oh, of course. With rest mass. No idea. Need a calculator for that. As the minimum energy is half the minimum energy. That sounds reasonable, but it's not. Okay. See, I can't answer these quickly, so they're good enough questions. Well, hey, you got one right, but that was pure luck. Okay, I got 22%, so that was not necessarily the best run. But here's the good stuff. No worries. The quiz tells me what I know and what I don't, which is often where a lot of diagnostic quizzes would end. Here's the good stuff. Snap provides a course. It's a course tailored for each exam board. And when I go into this thing, I get all of the videos. The videos are in order. They take me through the whole course, everything I need to know. So we have everything. We have these video courses, and what's nice is Snatrify has highlighted for me which things are important for me to go through and which things aren't. So based on how I did on the quiz, I definitely need to take a look at annihilation of matter and antimatter pairs, because I got that question wrong. And what's even cooler is when I go into a particular video, say I've gone into the antimatter video, I can even see which bits of the video I need to watch. I got the question on antimatter right, so we can skip ahead and go straight to the part on antiparticles, because that's the question I actually got wrong. So this is really efficient. This is a really good way to kind of streamline your learning and make sure you're always focusing on and picking off the bits that you don't know and not going over the stuff that you already do. So alongside all of this stuff, we prepared exam packs with kind of exam questions that we imagine could happen in the future, and some revision guides. Again, some kind of compressed, compiled notes for you to go through and try and remember all the stuff that we've been teaching in the videos. So we're really proud of this stuff. We've got a little dial to show you how far through our courses you've gotten. And yeah, so I'll just give you a look at the plans, and then I'll drop the code for the deals. And then, yeah, thank you very much. So, okay. let's have a look at some plans. Oh, sorry about that. Okay. Plans, here we go. So here's the idea. We've got three levels of subscription that you can go for. So you can take the basic. In the basic, you get access to our course. We're really proud of our course and you'll be able to learn from our course. Great, so we've got the bite-sized teaching videos. We've also got our exam walkthrough video. So I didn't mention this, but we've also filmed ourselves going through exam questions and explaining how we'd think about the answers and so on, along with these mini revision guides. If you take the pro account, then you get access to more. You get access to this self-marking quiz that we had. We get access to the smart adaptive learning stuff. So these are all these diagnostic quizzes that help you that essentially form the course around you. So you only do the stuff that you really need to be doing. This is where you really get to start like streamlining your learning, along with the predictive exam packs. And finally, if you're interested in the web classes and all of this stuff, if you want to come along and learn in this format, or also if you have questions that you need answering. So not only do we have web classes, but on the Ultimate account, we also have what are called drop-in tutor sessions. So in these, you can come in with any questions you have, and we as a group will go through them together. I'll talk us through them, and we'll try and figure out the answer. And so we can try and answer some of the questions that you have that you can't get answered. Good. Okay, good. So absolutely have a go at a free trial. And if you are interested in taking a look, then I can drop a code with you all. Okay, so here's the upcoming web classes. So I think you were asking about this. So we do have some maths and physics ones coming up, actually. I should have looked at this at the start. Ah, fantastic. Oh, I'm glad. Ah, that's really nice to hear. Okay, and there's the code. So yeah, any questions, let me know. I know there was a few questions before as well. Thanks very much for coming, everyone, and thanks for sticking around because I made that session a bit longer than it should have been. So cheers for making it a fun one. Cheers for answering and just having a go at answering all the questions. Never matters if you get it wrong. The best thing is always to try. So yeah, saw some really good stuff out there. Thanks everyone for coming. For the long wordy questions, I would say absolutely. I certainly used to break them down into bullet points. And maybe the kind of thing you're already imagining, but of course, long wordy questions vary so much that we probably have to be a bit more specific to have kind of more advice. But the one thing I can say is that it very rarely hurts to have bullet points. Yeah, thanks for a great section. Thank you all for coming. Thank you very much. I have to look at this mic from Sorted Guy. It's yeah, you've kind of piqued my curiosity with that. Yeah, thank you. Will there be physics live sessions? Yeah, roughly this time every month is the current plan. Of course, there's loads more web class sessions on SnapProvide. Your question's up. Yeah, we got that one. There'll be more live videos. Okay, I think that's everything. Thank you. Yeah, so that stuff, to be honest, the best thing I can suggest is going onto the website for that. So it'll give you a chance to trial things or to actually sign up properly and have access to the web classes. Since that wasn't a question, yeah, that's not one I'll answer. Okay, thanks very much for coming, everyone. I think I'll sign out there. I look forward to answering any other questions in the next sessions. And thanks very much. All right. Bye, everyone. Thank you so much for coming. Made it really fun. Cheers.